So we've got this statement that work is equal to FD cosine theta. And the theta in this equation is the angle between the force applied that you're considering and the direction of motion of that object. So we've got these three examples where you've got an object moving up, which is 180 degrees to the force of gravity. You've got an object moving down in line with gravity. That's a 0-degree angle of difference. And then you've got an object moving directly perpendicular, or even you could say normal to gravity there at a 90-degree angle to the right. If we run through cosine of these three angles, so cosine of the angle 180 is equal to -1. Cosine of the angle 0, oh, I won't say theta, just need 0, equals +1. I'll draw a positive to reinforce that. And then cosine of the angle 90 is equal to 0. This gives us three statements. Forces in line with the direction of motion do positive work, +1, positive force times distance. It'll be the product of those two. How much work will be dependent on the force and the distance, but we know it's positive if it's in line. Forces at a 180-degree angle or opposite direction to the direction of motion will do negative work because the cosine of 180 is -1. All right, so the last statement is that if it is a force is at a 90-degree angle to the direction of displacement, it is doing no work on that object. So for instance, if you're moving an object along a plane, then gravity and normal force aren't doing work on it because they're at 90 degrees. So we'll look at that exact example in just a second. So this statement right here just helps us see that relationship, that in line is positive, opposite direction is negative. It will take away energy, and then completely out of line, like as far out of line as possible, a 90-degree angle will do no work. So I'll erase these statements right here so I have some more space. And we will then remind ourselves that what's the unit for work? Work is measured in joules. So that is Newton meters from these two units, and that equals a joule. What's the other thing that has the unit of joules? Equals energy. And this is where our relationship begins for the work energy theorem. So the idea is, I told you, positive work is in line, negative work is opposite direction, and no work is perpendicular. The positive and negative deal with the energies either added or subtracted from your object. So we're going to make this new statement, and this is the work energy theorem. So if you write nothing down today, you need to write this down. Net work, not like the network, but all of the work from all forces. So if you have multiple forces acting, we'll do an example with two forces, you'll see what I mean, is equal to change in kinetic energy. So it changes the energy, and it's going to change the energy of motion. I want you to think about gravity again. Now I'll ask the question again. Why does the object slow down when it moves upward? What's the degree between its direction of motion and the direction of gravity? It's 180 degrees. Cosine of 180 degrees is -1. So however far it acts over, it does negative work in that direct or over that distance. Negative work, well, if the left side of this is negative, negative work equals negative change in kinetic energy. Well, are you going to change the mass here? Does the mass change of the object that's moving through the air? No. So what's the only thing that could change to make the kinetic energy change? What's the other term in kinetic energy? Mass and 1/2 m velocity. So really what you're going to see is a negative change in velocity. So then a positive network will do an increase or positive change in velocity. It will make it speed up. This is pretty much always the case. All right. So we'll just do a quick example so you can see what this looks like. We've got a box on a level surface. We're going to ignore gravity and normal force. Why can I ignore gravity and normal force? Because I'm going to be pushing to the right. I'm going to apply a force to the right of 25 newtons. So if you notice, gravity is perpendicular, normal force is perpendicular. They're not going to do work on the box as we move it sideways. I'm going to say that I'm going to move this box over 10 meters. So it's going to go 10 meters to the right, and it's moving to the right. So let's just look at this equation. Net work equals change in kinetic energy. I want to know how fast is this box moving after 10 meters of a 25 Newton push. So your initial thought is, I don't know. All right. I will tell you that this is a 10 kilogram box. You could do this with forces. You could say, all right, well, let me figure that out. Well, F equals ma. If I want to know how fast the velocity is, I'd have to know, well, distance. I could do some kinematic. You'd have to use kinematics and dynamics to answer this question. Or work energy theorem handles it immediately. So let's look. We've got a force, a distance, and a mass, and I'm looking for a velocity. That seems like, and I'll just write this right here just to remind everybody, Ke equals 1/2 mv squared. That's 3 out of 4 of the possible variables that show up in this relationship here. So net work equals FD cosine theta. There's only one force, so we're only going to look at that one force, equals 1/2 m change in v squared. All right, that's really what that means. It's going to be the change in your velocity. So I can take that change out if that makes you more comfortable. Erase all that, and I could write it as change in 1/2 mv squared, which is change in kinetic energy. I've just written the math versions of this statement right here. So if that's the case, what's the direction of what's the angle between the direction of motion and the force? 0 degrees. So this is going to be positive work, right? That should make sense. We're also going to say that it starts at rest. All right. That way you don't have to be like, well, if it changed its velocity, I don't know what it started at, so I don't know what its final is. So we're going to start at rest. We're going to push to the right. It's going to move to the right. So force and direction are in line. So positive work is done. We should expect the velocity to do what? To go up, to accelerate. And this is actually why forces cause accelerations, because it does work. All right. So we then look at that relationship. How much work does it do? Well, FD. What is force times distance here? What's 25 times 10? 250 joules. So 250 joules of work has been done, and that is equal to the change in kinetic energy. Well, how much kinetic energy did it have to begin with at rest? 0. So it increased its kinetic energy by 250 joules. Well, proportionally, what does that mean for velocity? That's dependent on its mass. So let's look. So 250 equals 1/2 mv squared. Its m is 10. Velocity there, we don't know yet. We'll solve for that in a minute. So how do I solve for v? I got to get rid of what's attached. Multiply by 2, divide by 10. All right, so if I multiply by 2, I get 500. Divide by 10, I get 50.
Hey, Mr. Sellers, do you mind if you write that out so I can, use it as a reference point, writing it out when you multiply it by 2, divide by 10, if that's okay?
So we're going to multiply this by 2.
And you said it'd be on your...
Divide by 10. Yes, it will be. Equals v squared. So we do that. We find 50 equals v squared. How do I solve for v? Take the square root of 50. What's the square root of 50? 49. 7. So it's going to be just over 7. The value ends up coming out to be 7.07 meters per second. All right, so let me adjust this. We're going to add another force. Same exact problem. Okay, same exact problem, except for now, we're going to add in 10 newtons of friction. All right, so now we're on a friction surface. Friction has 10 newtons of force. All right, so you might think, but what do I do now? I want to remind you that this states net work. Just like we had net force, where you had positive force, negative force, you add them together and you'll have some left over, and the sign will tell you direction. Same thing, because it's vector. It depends on force to get work, right? So we're going to have 10 newtons from this. So over here, I'm going to do the work due to friction is equal to the force of friction times the distance over which it acts times the cosine of what's the angle between friction and its displacement. It's moving to the right, friction's to the left. That's 180 degrees. So that's going to be -1. So it will be negative FD. All right, so what's the force? 10. What's the distance? 10. And it is the whole thing is negative. So that's negative what? -100. And then what's our unit? Joules of work. So friction did -100 joules of work on our box. So what's my net work done by all the forces in the direction of or along the plane of motion? So we're going to take the 250 joules that the push did. We're going to subtract out the 100 joules worth of energy that friction took out. And so what we'll be left with is 250 plus -100 equals 150. This is now our net work, and we can now calculate our new velocity. So how much slower would it be going if it had 10 newtons of friction? We set that equal to 1/2 10 v squared. We would take 150, we'd multiply by 2, divide by 10 to get rid of that 1/2 and that 10. This would equal v squared. So if you notice, that's going to be 300. 2 times 150 is 300. Divided by 10 is 30. That makes sense? So it'll be 30 equals v squared. So v equals the square root of 30. And if you knew that off the top of your head, I'd be impressed. It's going to be a little bit bigger than 5 because the square root of 25 is 5. It can be less than 6 because the square root of 36 is 6. It's between 5 and 6. So should be like 5.4. It should be closer to 5 than it is to 6. Is that right? All right, square root. Oh, that's squared. Square root of 30. 5.48. There we go. So conceptually, I want you to think about this. Does this not make sense? Doesn't this make sense? The idea that friction will take energy out of the system, and that's why friction takes away speed. So we've been talking about friction conceptually without ever talking about how it does negative work. Now, whether you noticed it or not, I totally said that a couple times, like multiple times. I said it takes energy out of the system. We had never talked about energy at that point, so it was probably meaningless. But friction does negative work and thus slows things down. All righty? So these are the basic concepts of the work energy theorem, that the net amount of work will be equal to how much kinetic energy changes, and by extension, how much the velocity of that object changes. So if I'm going to erase all this, you guys good? You good? I'm going to clear this. So what we're going to do now is we're going to go take some data. I told you you needed a second piece of paper, right? Get that second piece of paper out. You're going to create a chart for me that will have force, distance, velocity. You're going to have a second chart as well. The force you're going to start with is 115 for all of them. That is the starting force. So you can just go ahead and write in 115 for that first chart. There will be 5 data rows. Yeah, that word wouldn't come to me. All right. The distance will be 10 20, 30, 40, 50. So you're going to do the 5 trials, and you're going to have to calculate velocity. The velocity will be every time 10 meters over time, the photo gate time. It'll be one of the only numbers that changes throughout the simulation. So it'll be 10 meters every time, but the time will change in each trial. This will make sense once we see the trial, okay? Then the second chart needs to be force, distance, velocity, same chart. This time, distance will be 20, and I only want you to take 3 data trials. 20, 20, 20. You're going to keep the distance the same. I want you to increase the force. The first one will be 115. I don't exactly, let me see what the next one up is. Reset it. 30. Okay, it goes up by 15, so that'll be easy. Yeah, that is right. So it'll be 115, 130, 155. So you'll write those 3 down, and you're going to have to calculate the velocity, and the velocity will, again, be 10 meters over whatever the photo gate time it gives you. The photo gate measures in milliseconds because this happens quickly. You will divide whatever number it gives you by 1,000. So if you've got that set up, let's go take some data so that you can answer the question. So you will have a summary to follow this assignment. You'll do the assignment, take the data so that you can refer to the relationship. And the summary will be, talk about what we talked about on the notes, work energy theorem, the relationship that positive work increases speed, negative work decreases speed, that work is dependent on the direction of force and the direction of displacement. And then relate it. So that's your statement. That's your claim of the relationship. Then you'll cite evidence from your data. You'll say that when I increased distance but kept force the same, I saw velocity do this. When I kept distance the same and increased velocity or increased force, I saw velocity do this. This suggests either positive or negative work was done because velocity either increased or decreased. Does that make sense? And then you'll wrap it all together. You'll have 6 sentences, easy if you follow that statement. Explain work energy theorem, cite evidence from the lab that says, well, look, here's the proof, and then kind of make a conclusionary statement. So we're going to head to the lab. The lab is the link that says work energy theorem. So it's right here. You're going to go to that link. You're going to pull it up. You're going to hit begin. I want you to notice the sliders. You will not touch the mass. The mass won't change. So keep the mass the same. For your first 5 trials, you keep the force the same and you change the distance over which the force acts. Let me show you how that works. You have distances along this right here. You will hit shut off when you reach the desired distance. So at 10, you'd stop it there. At 20, you'd let it run. And you'd stop it as close to 20 as you can get it. So like that's perfect, but that won't happen every time because you got Chromebooks. Now, this is the part you're probably concerned with. This distance here is 10 meters. 70 to 80 is 10. The photo gate time is given to you in milliseconds. So what you'll need to do is divide this number by 1,000. Or, if you know what that means, move the decimal point to the left 3 times. So this is 1,194 milliseconds. Or 1.194 seconds. If I move the decimal 3 times to the left, it gives me how many seconds it is. So for instance, if I let this run, I'm just going to let it run to 40 because I know it'll drop it below a second. 40 and 50, it's kind of hard to stop on the line. Try your best. So this will be 0.85 seconds. It's less than a second, which is why it gives it to you in milliseconds. Okay? So then for the second set of trials, you're going to keep the distance of 20 meters the same. You're going to run a trial, increase force, then run it. I was a little bit off, but that's okay. If you're within about a meter or so, you should be all right. You'll take that data and look at it there as well. So that is what you're going to do just to make sure we see the summary. In this assignment, you're going to use the relationships we discussed, which came from the data collected in the lab. I want a 5 to 6 sentence explanation of the relationship between the work done by the fire extinguisher and the energy that Wally has at the end. Specifically, what did you notice about the relationship between the change in speed Wally has as you increase the distance over which the same force acts? That's the first 5 trials. Subsequently, what did you notice about the speed Wally has in the trials where you increased the force but kept the distance the same? That's the last 3. Make a claim about the relationship, cite evidence from the data, and then explain your reasoning. That would be a good 6 sentences. 2 sentences per, you're good to go. All right.